Okay, welcome back to the IR spectroscopy class. Uh, in this class, we are going to start discussing the vibrational frequencies of certain functional groups as well as the vibrational frequencies of bonds that make up the overall molecular structure or its the overall molecular skeleton. So we call this one as group frequency analysis. And in order for this one to make in order for this process to make it easier, we're going to divide the vibrational frequencies into certain separate regions, which we have already seen when we discussed the fingerprint region as well as the group frequency region. Okay, so starting from 400 to almost 1400 or 1600 centimeter inverse, the vibrational frequency region comprises of vibrations of carbon-carbon single bonds, carbon-nitrogen single bonds, carbon-oxygen single bonds, and carbon-halogen single bonds. So this one is a region which encompasses the vibrational frequencies of single bonds. Again, the region from 1600 to 2000 centimeter inverse includes the vibrations of carbon-oxygen double bonds, carbon-nitrogen double bonds, and carbon-carbon double bonds. So this one is double bond frequency region. And the region afterwards, starting from 2000 centimeter inverse up to 2700 centimeter inverse, this narrow region deals with the vibrations of carbon-carbon triple bond, carbon-nitrogen triple bonds, mostly triple bond vibrational region. And the region extending from 2700 centimeter inverse all the way up to something like 4000 centimeter inverse are basically dealing with the vibrations of bonds that are connected to hydrogen, lighter atoms such as hydrogen. So such as the vibrations of functional groups such as OH, hydroxyl, NH, and CH. Okay, so if you remember this general trend, it will be easy for us to discuss the group frequency analysis. So in order for doing the group frequency analysis, we shall be dealing with different types of molecular systems and functional groups. We will first start with the simple hydrocarbons, linear hydrocarbons such as alkanes, alkenes, and alkynes. When we start with alkanes, mostly you will have to remember that alkanes generally are composed of carbon-carbon single bonds. So mostly bonds that are being connected by similar type of atom. So mostly the electronegativity difference between the atoms is negligible there, and therefore the bands would be really weak. The carbon hydrogen bond, due to the relatively small electronegativity difference between carbon and hydrogen, is also again not much of a polar bond. It's actually a kind of a relatively non-polar bond. So the electron density distribution is not much polarized onto either of the atoms. So basically the dipole moment of this bond is relatively small. So this constitutes vibrations that are of medium intensity. Okay, so if you consider each of the group frequencies given in centimeter inverse, the first one is CH, stretching vibration. This one usually appear between a region of 2800 to 3000 centimeter inverse, and in simple alkanes. But if you consider ring systems such as cycloalkanes or cyclopentenes or cyclopropanes, then the strain in the ring system may bring the CH stretching frequency to a higher frequency. So keep this fact in mind. And for methylene type vibrations, CS2 vibrations, and for this one appears, the methylene bending vibration or scissoring vibration appears at a frequency of 1465 centimeter inverse, whereas the CS3 bending vibration, methyl bending, symmetric bending vibration appears at around 1375 centimeter inverse. And the rocking motion of 4 or more CS2 bonds, such as the one here, appears at around 720 centimeter inverse in the case of long chain alkanes. And this carbon-carbon single bond band is not usually, as we said earlier, is not much of a polar bond between carbon and carbon. So the vibration of this symmetry stretching vibration of this one does not actually give a discernible or a visible intense peak. So this one is not much of great use for getting molecular structure information. So we have seen this if you look at the uh, spectrum of this simple alkyne octane, so this color coded areas gives us an idea about the different types of bonding in this molecular structure, where this blue region deals with carbon hydrogen bonds. Okay, so the bonds that are given in the blue are carbon hydrogen bonds, whereas the bonds that are given in the red region are mostly carbon carbon single bonds and carbon hydrogen bonds related to CS2 in here. Okay, so we will be mostly dealing with the stretching and bending vibrations of these bonds. So the this one is an sp3 hybridized carbon, so the sp3 ch stretching vibration of the octane system in here usually happens between a range of 2800 to 3000 centimeter inverse, and that means mostly the carbon hydrogen bonds of methyl system shows up vibrations between the region of 2800 to 3000 centimeter inverse, whereas the carbon carbon stretching frequency and its bending frequency usually appears between 1360 to 1470 centimeter inverse, which usually comes around this region, which is, these are really weak peaks. And the carbon carbon bond between the CS2 part of the linear alkane usually comes around 1450 to 1470 centimeter inverse. That means somewhere here. And the carbon carbon bond vibration between CS2 and CS3 usually happens around 1360 to 1390 centimeters. That is this particular band. So this one is the carbon carbon vibration of CS3 CS2, and this one is the carbon carbon vibration of CS2 CS2. Okay, so this one is usually a simple spectrum which can be readily interpreted if we get an assumption that, or if we have an intuition that this one is a simple alkane system. So look at the band structure, look at the band position, look at how they are being shown in the IR spectrum, and get a taste of what kind of shape the IR spectrum could be happening for a normal alkane such as octane. Okay, and if the region between 1400 to 1350, that means between 1350, okay, right here, somewhere around here, 1315 up to 1400, this particular region, okay, this narrow region, if this region, if it is not contaminated by any kind of other kinds of vibrations, then that the peaks in that particular region could tell us a little bit more about the types of alkyl groups in the molecular structure. So say for example, if we have a methylenic system, okay, CS2 system here, the scissoring vibration of this methylenic system could be showing up a peak at around 1465 centimeter inverse. Okay, and if we have a methyl system in our molecular structure, then the asymmetric bending, okay, so asymmetric bending means these two bonds bend towards each other, whereas this bond bends away from this bond. Okay, so this asymmetric bending of a methyl group shows up a peak at around 1450 centimeter inverse, and usually the scissoring vibration of the methylenic system and the asymmetric bending vibration of the methyl system usually overlap, and sometimes when they overlap, it's not really easy to discern or distinguish which band is due to which vibration. But one of the good thing about the vibrations of methyl group is that the symmetric bending of methyl group usually gives a peak a little bit further away from this vibrational frequencies. This symmetric bending vibration, the peak corresponding to symmetric bending vibration usually shows up at around 1375 centimeter inverse. Okay, and again, if the CS3 group, if there are two CS3 groups which forms a geminal dimethyl system such as the one here, then instead of just one single peak, the symmetric bending of these two methyl groups will give you two peaks, one at 1370 centimeter and one at 1380 centimeters. So two peaks separated by around 10 centimeter inverse. So these are characteristic signature peaks of germinal dimethyl methyl groups bending vibrations. Okay, and again, if there are three methyl groups that forms a tertiary butyl system, then the symmetry bending vibrations of these methyl groups will again give us two peaks, one at around 1370 centimeter inverse, but the second one at around 1390 centimeter inverse. So this will tell us, these vibrations will tell us some details about what kind of alkyl groups are in the molecular structure, whether it's methyl or methylene in the molecular structure. And then moving on to the case of alkenes. The spectra of alkenes are slightly a little bit more complicated compared to the spectra of alkanes, because we will be seeing carbon-carbon double bonds asymmetry stretching vibration. Okay, normally the carbon-carbon double bonds symmetry stretching vibration, if both the carbons are in a equivalent chemical environment, then the symmetry stretching vibration will not give us usually an intense peak. So the asymmetry stretching of the carbon-carbon double bond is usually a more useful peak in terms of finding out the molecular structure. Okay, in addition, in alkenes we have got a sp2 hybridized carbon. So the hydrogen connected to the sp2 hybridized carbon, this CH bond stretching usually will give us a quite a distinguishable or a discernible IR peak. So that will tell us information about the alkene's molecular structure. But still, these bands are usually of weak to medium intensity. These bands are not really highly intense bands. So when you come to the group frequencies of alkenes, the CH stretching frequency of sp2 hybridized carbon usually comes up between a region of 3010 to 3095 centimeter inverse. So usually this one is a diagnostic for unsaturation of the molecular system. Okay, so this band can be seen in terms of aromatic as well as aliphatic alkenyl systems. Again, this CH bond of the sp2 hybridized carbon can undergo out of plane bending vibration. So we call this one as OOP bending vibration. Okay, especially this can be really seen in the case of aromatic systems such as benzene. Okay, so the phenolic or the benzenic carbon hydrogen bond can undergo out of plane deformation or bending vibration, and this signature band usually appears between a region of 650 to 1000 centimeter inverse, and this can be used to determine the degree of substitution on the aromatic ring systems, and which we shall be seeing later in our class. And the carbon-carbon double bond stretching vibration usually comes between a region of 1600 to 1660 centimeter inverse, and this vibrational frequency can be reduced by resonance or conjugation. Okay, and we have seen the effect of conjugation in our previous class. And the symmetrical carbon-carbon double bond does not give you any kind of peak. The vibrational transition does not happen in symmetrical carbon-carbon double bond because of the lack of dipole moment between the carbon-carbon double bond. Okay, and usually carbon-carbon double bonds which are involved in a trans configuration, trans isomer, gives a peak which is weaker than the IR transition of a carbon-carbon double bond in a cis isomer. If you need to discuss the special case of a linear alkene, then let's take the case of a terminal alkene such as 1-octene, where we have got the carbon-carbon double bond or the vinyl double bond on the terminal carbon atoms. So for such a system, the carbon-carbon double bond stretching usually is weak, and the intensity increases with the substitution. Okay, and this can be observed between 620 to 1680 centimeter inverse right here. This sharp peak is due to carbon-carbon stretching vibration. Okay, and the vinyl CH, the CH bond shown in blue shading here, and this vinyl CH stretching vibrations usually occurs between 3000 to 3100 centimeter inverse. This sharp in here is due to the CS stretching of the sp2 hybridized carbon in vinyl functional group. And this sorry this uh, group of bands, this one is similar to the spectrum we have seen in the case of normal alkanes. So these bands are due to the carbon hydrogen stretching frequencies of sp3 hybridized carbon. We have got sp3 hybridized carbon in the octane system here. So these are due to the stretching vibrations of the hydrogens connected to the sp3 hybridized carbons in the linear alkane chain here. Okay, and this typical band is due to, as we have seen in the previous spectra of normal alkane, this band is due to the carbon-carbon single bond stretching in the alkane part of the molecule here. Okay, so when you're looking at the vibrational frequency of the CH bond, it's very important, or it's very, sometimes it could be confusing to separate the carbon hydrogen bonds vibrations of alkanes, alkenes and alkanes. So in order to make it easier to distinguish, keep in mind that if the vibrational frequency, usually this particular band, if this one comes above 3000 centimeter inverse, it's usually the carbon hydrogen vibrations of a sp2 hybridized carbon, okay, such as a vinyl carbon hydrogen bond, and or alkynyl. Okay, and again if the band appears below 3000 centimeter inverse, then it could be due to the carbon hydrogen stretching vibration of a sp hybridized carbon or an sp3 hybridized carbon. Okay, see the case of trans 4 octane. So you can see that the carbon-carbon double bond is almost in a symmetrical environment here. So you may not be getting so much of a dipole moment for this double bond. So any transition that could be occurring by the vibration of this double carbon-carbon double bond would be weaker. Okay, really weak, and or you may not at all see any kind of band due to the stretching vibration of this carbon-carbon double bond. So if you see the spectrum here, you can see that the carbon hydrogen vibration of sp2 carbon here, that means the carbon hydrogen bonds of these two carbons here can be seen as a very weak band right over here. Okay, so this one is very weak. Again, this large band system in here, highly intense band system in here, is due to the stretching vibration of the carbon hydrogen bond of sp3 hybridized carbon on either part of the molecule, on either side of the carbon-carbon double bond. Okay, and you don't see the carbon-carbon double bond band which we have seen in the previous slide right here around 1650 centimeter inverse, and you cannot see it here. There is no band at 1650 centimeter, or the band is really weak because the carbon-carbon double bond is highly symmetrical. And you can see high intensity band at around 950, almost 950 centimeter inverse, which is due to the out of plane bending vibration of the carbon hydrogen bond of the trans system here. Okay, the carbon hydrogen bond on this carbon, or the carbon hydrogen bond on this carbon, could bend out of the plane of the molecule. Okay, so this one is called the out of plane bending vibration of the trans carbon hydrogen bond system in here. So that could give us this typical band. If you take so far we have seen only linear alkenic systems, but if we consider the case of cyclic alkenic systems such as cyclohexene, then you can see that the spectra is quite complicated compared to a linear simple alkenic system. Okay, alkenic hydrocarbon. So here you can see several bands in here. One of them is this sharp band, which we have not actually seen the previous spectrum here. This sharp band is due to the carbon hydrogen stretching vibration of the sp2 hybridized carbon in the cyclohexene system here. So these carbon hydrogen bonds on the sp2 hybridized carbons, when they stretch out, they give rise to this particular high intensity band. Okay, and again, now you might be able to distinguish this band as the band due to the CH stretching vibration of the sp3 hybridized carbon of the rest of the part of the molecule. Okay, and this band right over here, this sharp band at around 1650 centimeter inverse, is due to the cis C double bond C stretching vibration. Okay, this double bond can undergo a kind of vibration, such as this part is kind of a cis, is in a cis configuration. Okay, and this CS2, this vibration, this typical band is due to the CS2 bending vibration. You have got 1 2 3 4 CS2 groups in here, so they could bend out of the plane, and this bending vibration could give rise to this typical medium intensity band. And this sharp band in here around say 1710 centimeter inverse, 720 centimeter inverse, is due to the cis out of plane bending vibration of the carbon hydrogen bonds of the sp3 hybridized, sp2 hybridized carbon system in here of the alkenic system here. Okay, so this one is again the spectrum of cyclohexane, which we have seen in the last slide. Compare this spectrum with the case of simple cyclohexane alkane. Okay, so you can see the difference. You don't see any band due to sp2 hybridized carbon hydrogen stretch here, you don't see that, but you see kind of band system right here due to the stretching vibration of carbon hydrogen bond of the sp3 hybridized carbon, such as the one here. And again, you don't see any cis C double bond C stretching vibration in the case of cyclohexane, and you guess why? Because there are no C double bond C bonds here. And again, you see some CS2 bending vibration, which is sharper here compared to the case here, because we have got a pure cyclic alkane system. And you don't again see any cis out of plane vibration, bending vibration for this system, because this vibration happens only in the case of molecules having only double bonds, and we don't have any double bonds here. Okay, so the spectrum is quite similar when you have a simple alkanic system. So in order to get a conclusive idea about the types of substitution or the kinds of substitution, and how these different types of substitutions influence the vibrational frequencies of the carbon-carbon double bonds, and its the CH out of plane bending vibrations in a carbon-carbon double bond system. So if you consider so these bands usually gives us the range in which the carbon hydrogen out of plane bending vibration can show up its peak in the case of an alkenic system. Okay, so for a monosubstituted alkene such as the one here, R is a functional group, so this one is a monosubstituted system. Then what you will be seeing is one strong band at around 900 centimeter inverse, okay, and another strong band at around 1000 centimeter inverse. And in the case of disubstituted system, we have three different possibilities: cis 1,2, trans 1,2, and 1,1 system. So if we have cis 1,2 substituted alkene system here, then we shall be seeing a strong band, a highly intense band in the range of almost 650 centimeter inverse up to 750 centimeter inverse. Okay, and for the trans 1,2 system, we shall be seeing a strong intense band for the CH out of plane bending vibration at around 950 centimeter inverse. And for the 1,1 substituted system, we shall be seeing a highly intense band at around 880 centimeter inverse. Okay, for the tri-substituted system such as the one here, we shall be seeing a medium intensity band between 790 to almost up to 840 centimeter inverse. For the tetra-substituted system, do we see a CH out of plane bending vibration? No, because there are no carbon hydrogen bonds in here. Okay, so this one will give us an idea about where we have to look for the CH bending by out of plane bending vibrations of alkenic systems. Okay, So if you consider this spectrum, okay, we have got uh, you know, this typical monosubstituted ethylene system here. So you can see the sp2 hybridized carbon hydrogen structure due to this hydrogens in here, right here. Then the sp3 hybridized carbon hydrogen stretching vibrations due to the carbon hydrogen bonds in here. And then then we what you see is a carbon carbon double bond vibration right here. Then you see two highly intense kind of doublet peaks around 950 and 1000 centimeter inverse due to the out of plane bending vibrations of the carbon hydrogen bonds on the vinyl system here. Okay, and for a trisubstituted system such as the one here, then you shall be seeing the band due to sp2 hybridized carbon hydrogen stretching vibration as well as the carbon hydrogen stretching vibrations of sp3 hybridized carbon here, but these bands are of medium intensity compared to the band system here. Then since we have carbon system here, we have got the carbonyl the carbonyl stretching vibration as a doublet here due to and you see two different frequencies here due to Fermi resonance due to the vibration right here. Okay, and the vibration right here is due to the out of plane bending vibration of the trisubstituted system here on the vinylinic carbon system here. Okay, so you can see the difference between the substitution pattern, or you can see the difference, how the difference arises in the peak pattern when we have different types of substitutions pattern on the carbons which are involved in carbon carbon double bond formation. Again, if we consider something like a cis disubstituted system such as the one here, then you can see that we have got a band at around particular waves this particular frequency, which is due to the carbon hydrogen stretching frequency of sp2 hybridized carbon, and this is due to the stretching frequency of carbon hydrogen bond of sp3 hybridized carbon. And this typical band which we have seen earlier is a sharp peak due to the carbon carbon stretching frequency of a typical cis isomer, and this one is the out of plane bending vibrations of all these functional groups which are being connected to or which are being arranged in a cis configuration around these ethylene carbons. Okay, which is a broadened single type of band here. Whereas if you have a trans configuration here, then in addition to this type, the bands we see here, we see a very weak band system here due to the carbon carbon double bond stretching vibration of a system, ethylene system in a trans configuration. We have already seen that the carbon carbon double bond vibration will give as a weak band in case of a trans configuration compared to a cis configuration. And this band system here will tell us details about the out of plane bending vibrations of the functional groups around the ethylene system here, which are being arranged in a trans configuration. So this band is basically due to trans or P vibration. Again, when we move on further into the substitution patterns of alkenic systems, we shall be seeing that we can see a hell lot of different varieties of different ranges of vibrational frequencies. When we start with a monosubstituted alkene system such as the one here, you shall be able to see two different vibrational frequencies at around 900 centimeter inverse and 1000 centimeter inverse. But for if the monosubstituted functional group, the functional group which we use to do monosubstitution on the alkene system, if it's a carries a lone pair electron density such as the such as chlorine, fluorine, or alkyl oxy functional groups, then this non-pair electron density or non-bonding electron density on the functional group can interact with the carbon-carbon double bond pi electron system here. As a result of this, what happens is we shall be seeing one band at around 800 centimeter inverse, which is pretty usually strong, and another band at around 1000 centimeter inverse. Okay, But when we have a monosubstitution pattern on the alkene system with a double bond rising out from the functional group, such as in order to extend the conjugation further, such as carbonyl or C triple bond ends. For example, this G double bond is carbonyl C double bond or system, or C triple bond end system, then we shall be seeing one band at around 1000 centimeter inverse and the other one around 950 centimeter inverse. So this is usually the frequency ranges for substitution pattern, monosubstitution patterns on alkene systems. And if you consider double bonds which are a part of ring systems, we can then talk about two types of double bonds. One is endocyclic and the other one is extracyclic double bonds. Okay, so if you consider endocyclic double bonds, that means double bonds which are coming inside the ring system, then you can see different types of such cyclic alkene systems here, starting from cyclopropene to cyclobutene, cyclopentene, cyclohexene, and cycloheptene. Okay, so when you go all the way from cycloheptene to cyclopropene, the ring strain increases. So this ring strain can shift the carbon-carbon double bond stretching frequency, and you shall be seeing a trend here. So if when we go from cycloheptene all the way up to cyclopentene, the vibrational frequency decreases. Okay, but still these vibrational frequencies are quite large compared to the vibrational frequency of cyclobutene. Okay, and there is a typical reason, and which we shall be discussing shortly. Okay, but here again we shall be expecting that as the ring strain increases, the vibrational frequency should still drop down. But what we see on the contradictory is that for cyclopropene, the vibrational carbon-carbon double bond vibrational frequency is greater compared to cyclobutene. Okay, so this is kind of surprising. So what's going on in here? If you consider the carbon-carbon double bond vibrations, these carbon-carbon double bond vibrations may couple with the carbon-carbon single bond vibrations which are connected to the carbon-carbon double bond. Okay, so this coupling could change or influence the carbon-carbon double bond vibrational frequency. Say for example, if you consider the cyclopentene system here, which we have shown in detail at the bottom here, and if you see the stretching vibration of carbon-carbon double bond here, and the stretching vibration happens along this direction, and this typical vibrational mode may be represented by this typical vectorial arrow here. Okay, and the carbon-carbon single bond vibration of this typical carbon-carbon bond can be represented by two components, or can be resolved into two components. Okay, one component lying along the direction of the carbon-carbon single bond, and the other component which is perpendicular to the direction of carbon-carbon double bond. Okay, this one is this typical component. Okay, so these are the two resolvable components of the carbon-carbon double bond vibration, and you shall be seeing that there is no coupling between there is no possibility of coupling between these two vibrational modes, this typical vibrational mode of carbon-carbon single bond and this typical vibrational mode of carbon-carbon double bond. But whereas the vibrational mode of this carbon-carbon double bond and this typical vibrational mode of carbon-carbon single bond may couple to some extent because of the angle between this carbon-carbon double bond and carbon-carbon single bond is greater than 90 degree. Okay, almost close to 120 degree, and you shall see that this bond angle increases when we go from cyclopentene to cyclohexene and up to cycloheptene. So this coupling of the one of the vibrational components of carbon-carbon single bond with the carbon-carbon double bond increases as we go from a smaller ring all the way up to higher ring system here. So you can see a slight increase in the carbon-carbon double bond frequency when we go from cyclopentene up to cycloheptene. Okay, but once we come to the case of cyclobutene, and which is represented here, you can see that this vector represents the vibrational mode of carbon-carbon double bond, and the carbon-carbon single bond vibration is at an angle of 90 degree with respect to carbon-carbon double bond vibration. So the vectors which corresponds to the vibrational modes of carbon-carbon single bond vibration and carbon-carbon double bond vibrations does not effectively couple with each other. Okay, so this lack of this coupling reduces the vibrational frequency to 1566 centimeter inverse. But once we go again further up to the case of cyclopropene, then you can see that unlike the case of cyclopentene, the carbon-carbon single bond and carbon-carbon double bond angle gets reduced less than 90 degree. The bond angle is almost 60 degrees here between the carbon-carbon single bond and the carbon-carbon double bond. And you can see that the carbon-carbon double bond vibration mode can be represented by this arrow, whereas the vibration of this typical carbon-carbon single bond can be resolved into two components, one lying along this direction and the other one perpendicular to the vibration of the carbon-carbon double bond. So these two vibrational mode does not couple with each other, whereas these two vibrational modes, the vibrational mode of carbon-carbon, this typical vibrational mode of carbon-carbon single bond and this typical vibrational mode of carbon-carbon double bond can couple to some extent, and this increases the vibrational frequency to a value of 1656 centimeter inverse. So this typical ring strain and coupling of the vibration modes actually use these trends in the carbon-carbon double bond stretching vibrations. If an endocyclic double bonds comes in middle way between two fused ring systems, then the pi electron density here is being shared by both the ring systems here. Then the carbon-carbon double bond vibration would be shifted towards lower frequency, as if one further carbon is removed from the ring. Okay, and again, if you have some additional substituents, alkyl substituents on the ring system, that could dramatically influence the carbon-carbon stretching vibrational frequency. For example, if you consider cyclopropene, the carbon-carbon double bond vibrational frequency is 1656 centimeter inverse. But once you have an alkyl substituent here, so for example methyl group here, then you know that methyl group and any kind of alkyl substituent here, such as methyl group, would be an inductive electron donating group, and that would interact with the double bond here and therefore increase the carbon-carbon double bond force constant, and that would increase the vibrational frequency. So the greater the number of alkyl substituents, the greater would be the inductive electron donating effect onto the carbon-carbon double bond here, and that would greatly enhance the carbon-carbon double bond force constant and will increase the vibrational frequency further. Okay, and the same thing can be seen in the case of cyclobutene. For cyclobutene, the carbon-carbon double bond frequency can be observed at 1566 centimeter inverse. With the substitution of an alkyl substituent such as the one here, such as say for example methyl group here, the interaction of methyl group with the double bond through inductive effect will enhance the force constant of this double bond and will enhance the stretching vibrational frequency to 1641 centimeter inverse. And with the one more alkyl substituent here, the vibrational frequency will be further enhanced up to 1675 centimeter inverse. For the other counterpart, exocyclic type double bonds, such as the ones shown here, these four ring systems here, then you can see that with an increase in the ring size, the carbon-carbon double bond stretching frequency decreases. Okay, so you may compare this one with the increase in ring size of carbonyl systems we have discussed in previous slides. Okay, so what happens is, as we go all the way from right to left here, the ring size decreases, and when you consider the sp2 hybridized carbon right here, from where the exocyclic double bond starts off, then you can see that the bond angle of the carbon-carbon single bonds connected to the sp2 hybridized carbon gets reduced as we go from the larger ring system all the way up to the smaller ring system here. Okay, so in order for making this bond angle smaller, then more of p character 2p orbitals character should be contributed towards this carbon-carbon single bonds. Okay, so more of 2p character of the carbon, sp2 hybridized carbon, will be contributed in this smaller ring system towards these two carbon-carbon single bonds. So as the 2p character is being taken away from the 2p, the carbon sp2 hybridized carbon towards this bonds, the 2p character will be getting reduced in this typical pi bond system here. Okay, so this will reduce the strength of the pi bond here, but for the sigma bond, what happens is with the reduction in the 2p electron density, the apparent contribution of the 2s electron density on the sigma bond of the double bond system will increase. Okay, so the increase in the 2s electron character in the sigma bond will greatly enhance the force constant of the sigma bond involved in carbon-carbon double bond system here. Okay, so with the enhance in this force constant of the sigma bond here, the overall stretching frequency of the sigma bond will be getting increased. Okay, so for this typical double bond system, the enhancement in the stretching frequency is due to more of 2s electron character involved in the formation of the sigma bond, the lower dimension ring system here.